You are in the right room, as the title might say. It still is how shit works, but this time we're going to be talking about my mom. Now, before we talk about my mom, there are certain things that have to be put in their place, so we will start with this disclaimer. I love my mom. So everything I'm going to be talking about, if it seems like I'm making fun of my mom, I might very well be doing that, but it's all out of love. Everything is a slight exaggeration, but it's also kind of the truth. So hopefully this will resonate with some of you who have moms of your own. So if I were to have a conversation with my mom over some text medium, like SMS, WhatsApp, whatever it is you use here, in theory it should look a little bit like this. We have a conversation going on. Hello, son. Hi, mom. She gives me a bit of information. I reply. Like, it's a very nice linear sequence of sentences, events, messages that just makes sense, right? This is how it should be. Crucially, though, like if you look at the conversation, the text itself, by the way, is just made up, so don't worry about it. What's important is that this is a point-to-point communication. There's me, there's my mom, there's no one else involved. It's all in one continuous session or one sort of stream of consciousness, if you will. There's an explicit preamble or handshake. Hi, mom. Hi, son. There's stateful communication. So for any given message, each of the participants in the conversation already has some idea of what the conversation is about. Like, we keep track of the conversation on both our ends. There's an explicit termination, so sounds good, see you soon, love you, mom. You will notice that the order in which messages arrive is consistent with what you'd expect. So we have in-order delivery, and we didn't drop any messages on the way, so we have reliable delivery. This is what a good conversation looks like, one that makes sense. Unfortunately, the reality of talking to my mom is a little bit more like this. Why aren't you answering? I'm in a meeting. A ton of text. Confusion. Terror. Shock. Ruthless efficiency. Like, this conversation is super hard to track even as a participant. None of you have any chance in hell of understanding what is going on here. And me, as a participant in that conversation, I'm struggling to keep up. I'm struggling to figure out what the conversation is about, like what did I forget, what's important, what isn't. It's a mess. In this case, we have very few delivery guarantees. We have messages coming in out of order. So we have those two sentences where if you can't read them, they say, did you get the gift for grandma? We might meet at 7 o'clock. What is the order in which I'm supposed to be consuming these bits of information? Like the question, the comment, there is no ordering. It's also unreliable because the conversation started with, why aren't you answering? Well, why am I not answering what? Did you call me? Did you send a message? Like, what's going on here? We have very fuzzy session boundaries, so there's no hi, there's no goodbye, there are no explicit boundaries to this session, to this communication session. And the receiver is totally overwhelmed. The receiver being me in this case. Like, when I talk to my mom, especially over text, I tend to get overwhelmed because there's a lot of stuff to go through and I have to keep track of all of it, and I can't. This feels a lot like being dropped in the middle of 3 concurrent conversations where I'm one side of each of these conversations, but I have no idea what's going on. And if you think about it, this is actually quite amazing. Let's consider what worked. Okay, I had this very strange, totally incomprehensible conversation with my mom that left me very, very confused. But we could address each other. My mom has my phone number, I have hers. So if I text my mom on my cell phone, there's a whole slew of infrastructure on the way that takes that phone number, converts it into an IMSI or whatever modern-day standard cellular communication systems use. And there's a packet switching network that actually makes sense of that number and routes the packets to their eventual destination. But we don't have to think about that, right? It just works. Furthermore, we could communicate. We could actually send messages to each other. Routing is a very complex problem. If I if I build up a packet that includes a bit of text and I have a way of addressing that packet, like I have a MAC address or an IP address or some destination address with which to send it, just the act of routing these packets across multiple heterogeneous networks is an incredibly complex set of systems that are wired together in a way that actually works. The packet made its way to my mom's device. And we don't have to think about that either, because it just works. We could transmit and receive information. So radio is a very complex system in and of itself, right? The packets arrive at some base station somewhere that's connected to my mom's cellular phone or mine. There is no wired connection between my device and the base station, right? So you have some system of transceivers along the way that actually converts that stream of bytes, that message that I sent my mom, into radio signals that get received by the antenna on my device, get decoded and made back into a string of bits, which is pretty amazing if you think about it, because it just works. We don't actually have to think about it. So despite that conversation not making any sense, so many different, incredibly complex layers of systems actually worked just fine in between our two endpoints. And this is what I like to call the onion of abstraction. Right? We have layers upon layers upon layers of abstractions that we build on top of, and that allow us to just not think about how things work under the hood. And that is amazing. But something did go wrong, though, right? We had that conversation made no sense at all. Why? It made no sense at all because my mom and I failed to collaborate. My mom sent data faster than I was able to consume and process it. Right? I'm overwhelmed. I just don't know what to do with that plethora of totally intermingled details. My mom failed to retransmit data that I had lost. So for that particular conversation, my mom was asking me about the birthday party for my grandmother that I had either not known about or totally forgot about. It doesn't even matter what caused the fact that I did not know there's a birthday party going on. What's important is that my mom failed to retransmit the important data so that I can catch up on the important bits of the conversation. And there was no way to infer the correct order of messages, right? I received a bunch of texts. I don't know which came before which. It's very, very hard to make sense of a conversation that comes in totally with no explicit ordering, no ordering semantics in it. This is a problem. But have you noticed, despite the fact that we failed to collaborate, despite the fact that so many things have worked, we were having this conversation on top of a very well-proven, battle-tested system of communication, which is text messages. You probably use that system every day, and it generally just works for you. Because texting is reliable, and texting is ordered, but it didn't help. Right? You send messages to your friends over WhatsApp or whatever it is, they will arrive, and they will generally arrive in order. But that's still not good enough. It turns out that reliability, the ability to communicate in a reliable, semantically correct, sensible manner, is not the responsibility of the infrastructure. It is the responsibility of the endpoints or the applications, whatever it is that's sort of at the top layer of the protocol stack that we're building on top of. In this case, the app being me and the other app being my mom just failed to collaborate. And it was our responsibility to make sense of each other. The network cannot give you semantics that will mean the communication between your two endpoints makes sense. In the same way that HTTP, it might provide some semantics, but HTTP in and of itself isn't sufficient for a reasonable, semantically meaningful way to communicate between two services in your microservice architecture. This is known as the end-to-end principle, and the end-to-end principle is kind of the most important principle or the cornerstone underlying TCP/IP. And that is what we're going to be talking about for the next 45 minutes or so. Critically, though, what my mom and I were missing, what my mom and I need in order to communicate in a way that makes sense, is a protocol. And with that, we can move to how shit works TCP/IP. Or, if you've been keeping track, and paying attention, you might notice that actually we're not going to be talking about IP that much, but we are going to be talking about TCP, which is largely at the top of the protocol stack that you might employ in your day-to-day work. Before we get into the details, a second bit of full disclosure. I am very, very far from being an expert on networking or networking protocols or TCP or any of that stuff. I'm an enthusiast. I like learning about stuff. I am not an expert. This means that everything I tell you over the next 40 minutes will be grossly simplified. I'm going to be ignoring a lot of details. That means it might also be inaccurate, and it might be flat out wrong in some cases. My hope is to provide you with a good sort of baseline intuition around TCP, what problems it solves, and how it works. This is going to be very far from a university course grade course on TCP. And we'll barely scratch the surface because, as with everything, this is a huge topic. So we're just going to get some bare bone intuition about TCP out of this. We're not going to be getting the full picture. With that in mind, let's get started. If my mom and I need a protocol, and we need to design a protocol for communication between my mom and I, then we need to do some product management. We need to have some assumptions about what it is we can build on top of in sort of the ecosystem that we're in, and we need to have some requirements that our protocol needs to fulfill. So, vis-a-vis assumptions, we're going to be assuming a lot of existing infrastructure. So physical transmission, addressing, routing, all of these things we're going to assume are already there. The astute among you might notice that I just kind of described IP out of the TCP IP stack, right? So we're going to assume all of these things are there and they work. In terms of requirements, though, what is it that we're trying to achieve? So for the purposes of me communicating with my mom, the first thing we want is a bunch of delivery guarantees. We want to make sure that we don't have any dropped messages. We want to make sure that we don't have any duplicate messages. And we want to make sure that the messages arrive in order so that my mom, or myself in this case, can actually reason about the order of messages in a way that makes sense. Furthermore, we want a protocol that guarantees that the sender, which in that example was my mom, cannot overwhelm the receiver by sending just too much stuff. Right? The receiver has a certain capacity, has a certain bandwidth that they're able to actually consume messages in, and we want to make sure that the protocol adheres to that limitation and doesn't overflow the receiver. So, let us examine one very, very simple solution to the problem. It's super simple. If you send one packet at a time and await for an acknowledgement before you're allowed to send the next packet over, you're done, right? This solves all of our problems, all of them. We have in-order delivery because the network can only ever carry one message at a time, so things cannot be out of order when you already are able to only send one message at a time. Things cannot be dropped because we are waiting for acknowledgements. So this actually is a nice, clean solution to everything we need. Obviously, were that the case, we wouldn't be having this conversation. So this is clearly insufficient as a messaging protocol. Why not? Well, because it's very, very, very inefficient. What we want is a conversation that goes like this. If I have a bunch of things to say, I burst all of the messages that I need to send. I just put them on the wire and have the protocol deal with the delivery semantics, make sure that they all arrive in order. And then the receiver, my mom, takes that in, sends her own burst, going back and forth, right? As soon as I have something to send, I want to be able to send it irrespective of how big it is or how complicated it is. This is what we want. If we were to use that very, very simplified one packet at a time protocol, what we actually get is this. Yes, what we actually get is this. And obviously, this is a very fakey example, right? But you'll notice that things come in very, very, very slowly. And more importantly, the nature of the request response aspect of the protocol, because I only send one packet at a time, I wait for an acknowledgement, same goes for the other side, means that a simple conversation like, are you coming to dinner, like here's what you should bring, here's here are some details, could take hours and days, which obviously just will not work. It is totally inefficient. So if we go back to our requirements, right, we are missing a requirement that'll make sense, right? They'll give us the sort of efficiency we need. And we need to add a new requirement whereby we want to maximize throughput. We want to make as much use of the network as possible, given the demand, right? If a sender wants to send this much information and the network can handle that, we want to put it on the network altogether. If the sender wants to send this much, but the network can only accept this much, then we will split it up into packets and put those in order. But whatever the case, we want to maximize our utilization of the underlying network so that we get as fast or as low latency, high throughput communication as possible. And those two requirements, sender cannot overwhelm the receiver, and we want to maximize throughput. In the sort of network stacks that you're familiar with, those two requirements are generally called flow control. So when you see TCP flow control, this is what it means. It means that aspect of TCP that acts to maximize network utilization while taking into account back pressure, taking into account how much data the receiver can actually handle. So we have our assumptions and we have our requirements. Maybe TCP is the solution for us. So let's talk TCP, right? TCP solves these problems on top of the sort of computer networks that we know. TCP drives the internet as we know it. And let us dissect it a little bit, figure out how it solves those exact problems, and why we don't generally have to think about them anymore. So first of all, the stuff we all know, TCP is a transport layer protocol. It is point-to-point, it is connection-oriented, it is reliable, and it builds on top of IP. All of these things are the sort of idiomatic expressions that you can parrot at a job interview and probably get away with it. But in order to actually understand how TCP works and how it solves those problems, we need to go in a little bit deeper. Let's start with explaining what point-to-point means in this context. We have here a simplified pyramid of the protocols or the things that are in place in order for us to actually have a TCP connection. Right? We have a client and a server. They build on top of TCP. TCP builds on top of IP, and IP builds on top of some sort of physical network infrastructure, usually Ethernet. Right? Most computer networks that we work with today are Ethernet. It is worth noting, though, that TCP and IP do not assume Ethernet under the hood. Right? They are decoupled from the physical medium of communication. That's just a small tidbit. So for nomenclature, Ethernet deals with sending frames, decoding and encoding frames of data onto the wire. If we assume that, then next we have IP. IP gives us addressing and routing. And IP deals with datagrams. Okay, that is just the word they picked for the sort of messages that IP carries between hosts. And then TCP deals with segments, so that on top of all of that, what we end up having, the abstraction that we end up working with as we build our software, is a bidirectional byte stream. We don't think in terms of segments or datagrams or frames. At most, we are generally aware that there's packets going on, but what we actually get is an input stream and output stream abstraction. And you actually have that abstraction by name in most programming languages. So whether you use C# or Java, you actually have those byte input stream and byte output stream abstractions that you build on top of. And then there's the whole stack of things that is designed to make sure that from your point of view as an application developer, you actually get a bidirectional byte stream, but in fact, those byte streams are broken down into packets that get sent over the wire in various interesting ways. Next, we have connection-oriented. What does it mean to be a connection-oriented protocol? Well, the first thing we have to take into account is that the networks we build on top of are asynchronous. We just have packet switching networks. We have packets running around heterogeneous networks. They go from hop to hop. They get routed, right? The network is stateless, right? The router that routes your packets from your, whatever, your Mac through your wireless router to your internet service provider's station or exchange somewhere outside your house, to the bigger exchanges and all the way to the other side of the internet. Those don't care about what's in your packets. They are stateless. As far as they're concerned, there is a source, a destination, and a routing table, and they just route stuff along. They don't know anything about what's in your packets, and they don't need to know. They don't care that the packets all end up converging on the same TCP connection, and they don't need to care, right? They are stateless. TCP gives us a connection abstraction, a stateful phone call, if you will, between two endpoints. You have host A, you have host B, and it doesn't matter if the host is your iPhone or your server or a web browser or a client or an Elasticsearch client. It doesn't matter. You have two endpoints that want to talk to each other. One of them initiates the connection, initiates the phone call. And that's what a connection-oriented protocol entails. It means that a connection is an abstraction that is stateful. So when I pick up the phone and I call my mom, I initiate a connection. I don't have to do that on every message. We already have a connection. Once she answers and we start our conversation, we don't need to reiterate the data. We don't need to have that handshake over and over and over again. Critically, though, it also includes an explicit handshake and an explicit termination phase. When you give someone a phone call, generally speaking, you start with hi, and then you talk, and then you say bye, right? There is a nice boundary to the conversation. And the TCP connection abstraction includes that boundary very explicitly as part of the feature set that it provides for you. When a TCP connection starts, you might have already run across the term three-way handshake. That is how a TCP connection gets formed. Some host A in this case, initiates the phone call, sends a synchronized packet or SYN packet to host B. Host B receives that packet, sends back its own packet that both acknowledges the phone call and includes its own handshake, and then host A also acknowledges that. And you'll notice that just through that handshake, you can actually start measuring things. Critically, the thing you might want to measure is round-trip time. Round-trip time being the length of time it takes for a packet to reach from host A to host B and back again. And you cannot measure just one direction because the network is asynchronous. You don't really know what happens to the packets in transit. All you can know is how long it takes for a full round trip between yourself and the other host. And that is a thing you measure. Generally speaking, you term that RTT, or round trip time, and that has some nice benefits to measuring that. TCP is also reliable. So as you all know, in an IP network, packets can get dropped, reordered, they can get duplicated, and they can get delayed. All of these things not only can, but do happen in any packet switching network by definition. So TCP gives us, through that connection abstraction, a bunch of mechanisms to deal with that. TCP handles the ordering of events. So if two packets come in out of order, it is TCP's business to actually provide them to you, the consumer, in the correct order. TCP also handles retransmission. So in case a packet gets dropped, it has to be resent, right? That is part of the protocol. And all of that might seem simple, but actually the way that it works is quite complicated, and that's what we're going to be discussing next, even though it is quite a big topic. So again, we're only going to be scratching the surface. Let's talk about TCP Flow Control. We have what appear to be two conflicting goals. We want to make as much use of the network, but we also want to not overwhelm the receiver. So what we what we basically want is we want to send as much data as we can from the sender to the receiver, and we want to have a back pressure mechanism whereby the receiver advertises just how much data it can take in, and we need the sender to take that into account. In order to do that, we actually need the two endpoints to collaborate. So TCP is a collaborative protocol. We don't have in here, in these diagrams, in these pictures, any central authority that tells host A, well, dude, slow down a bit, you're overwhelming host B. There is no central authority. All you have are two endpoints and the protocol stacks they have in order to solve this problem. So by definition, TCP has to be a collaborative protocol where host A and host B collaborate so that they achieve flow control in a way that maximizes our use of the network. And the way this works is through TCP Sliding Windows. And this is where things get a little bit hairy, but also interesting, I believe. There is no way of avoiding that, sorry. So, TCP sliding windows, right? We have a timeline, we have the sender, we have the receiver. The sender is at the top in yellow, we have the receiver at the bottom in orange. And we have the message, hello world, which, does anyone here not know this message and is not run across it like a million times? This is the canonical example of programming languages. So why not? We have it for TCP as well. Right? This is the message that we want to send from A to B. We also have those two numbers below. The receive window size is the number of packets, or my bad, the number of bytes that the receiver advertises as being willing to accept, right? The receiver tells the sender, I can accept up to 4 bytes at a time, right? 4 bytes, of course, is a made-up number. It's super small. It's totally useless, but for the purposes of this discussion, it's close enough. And there is also something called MSS, or max segment size, which we will circle back to later. So to start with, because we know that the receiver can accept up to 4 bytes at a time, and the maximum segment size tells us how many bytes we can send within one TCP segment, we will be circling back to that, right? I can only send 1 byte per packet. So I can send 4 packets in. I pick the first 4 letters, and I emit a packet for each one of those, right? So we have 4 packets, and each packet gets a sequence number. Right? We have packet 0 with the letter H, packet 1 with the letter E, and so on and so forth. So on what's called a sunny day scenario, under normal operation, at some point the receiver will start getting packets in. Right? The network has its own latency, it takes a bit of time, but at some point the receiver will have started to receive those packets. And it starts sending back acknowledgements. Right? So it received the first packet with the letter H, it sent back an acknowledgement, received packet sequence number 0, and the sender, having received that acknowledgement, knows that it can slide the window and start sending in more and more and more data. Right? So it moved just the 1 byte, and now the sender can introduce another packet into the mix, in this case, the letter O. And it just keeps on happening like that. Now, one crucial element of the equation is that these acknowledgements are what's called cumulative acknowledgements. The sequence number that the acknowledgements include is the last fully acknowledged, fully processed byte in the stream. What this means is that if the receiver has taken in a bunch of packets, but there is a gap, right? Let's say it took in packets 0 and 3. Right? It will still only ever send acknowledgements for packet 0 for as long as it did not receive the next one in order, which is 1. This is how TCP makes sure that you don't get packet delivery out of order. Right? So the acknowledgement only ever includes the sequence number for the next expected byte in the stream. So this just carries on. This is the sunny day scenario. What happens when shit hits the fan? What happens when things do not work properly? Well, let's assume we have packet loss. We sent out those same 4 packets, H, E, L, and L, the first 4 letters of hello, and also the word hell, just for kicks. And let's say the packet for E never showed up. Right? Why did it not show up? There's a myriad of reasons. Maybe one of the network switches on the route is overflowing and just can't handle as much information. Maybe my neighbor's dog chewed on the network cable. Maybe aliens started blasting Earth and took out like one of the big exchanges. I don't know. Like there's any number of reasons why that can happen. Let's assume it did. Right? The packet for E never got through. So what would happen? Well, we sent out 4 packets. Only 3 were received, but the receiver did take in 3 packets, so it does send out 3 acknowledgements. But as I mentioned before, those acknowledgements can only include the sequence number for the last expected fully processed packet. Right? If I, as the receiver, have received H, then I can acknowledge sequence number 0. Then I receive L, which is sequence number 2. I cannot acknowledge it because I haven't seen 1 yet. Right? So I can only acknowledge up to the sequence number I've already observed, which in this case is 0. Now, you might ask, then why send multiple acknowledgements for the same sequence number in the first place? And the answer to that is because acknowledgements are packets and packets get dropped. So I, as a receiver, have no way of knowing if my acknowledgements actually made their way back to the original sender. So I just reissue them with the same sequence number, and that's fine. Hopefully, the receiver will have accepted one of the multiple acknowledgements I ended up sending. But I do send an acknowledgement in every received packet. Now, how does TCP deal with retransmission? Well, it does this through 2 mechanisms, and those 2 mechanisms are complementary. The first mechanism is for every packet sent, the sender starts a timer. It starts measuring time. How long has it been since that packet was sent, and how much time do I allow for that packet to be acknowledged? Now, the retransmission timeout, the number of whatever, milliseconds, microseconds, whatnot, that the sender is willing to wait for an acknowledgement is actually quite a complex topic in and of itself. How to determine the right RTO is complex, but critically, it mostly relies on the round-trip time. If I know that on average, it takes 100 milliseconds for a packet to reach my destination and back, then it can be assumed that if I wait, say, twice that long and have not received an acknowledgement, then the packet was somehow lost in transit. It's just a reasonable assumption. So I kick off a timer on every packet, and if I have not yet received an acknowledgement within that span of time, then I retransmit that packet, which I'm allowed to do because the sender keeps track of the sequence number. It knows what to do in case it gets the same packet twice. It can just drop it, or if it didn't receive that packet in the first place, it can now consume it. And then, assuming everything works as it should, then the packet got retransmitted, the receiver acknowledged that, and the window can just move forward. And that's why it's called the sliding window, because it slides along with the data that gets transmitted. Now, you'll notice that this is actually quite wasteful. Waiting for a retransmission in certain situations can be very bad. And the retransmission timeout, I think, was originally set by the spec to be 3 seconds, and then it was adjusted to 1 second. But whatever number it is very, very slow. If you get a packet drop every now and again, you might just delay the transmission of everything in your byte stream by that amount of time, which can be quite considerable. So there are ways around it. The second mechanism TCP employs, which can be thought of as a very, very important optimization. That's what keeps our networks chugging along, is called TCP Fast Retransmission, or the Jacobson algorithm. Now, what this does is it keeps track of the acknowledgements that we get from the receiver. If I, as the sender, have sent a packet, right, I've sent E, and I kicked off that timer had not yet elapsed, right? It'll elapse at a certain time in the future that we don't care about. But I have seen a number of retransmissions of, I have seen a number of acknowledgements for the same sequence number, then I can infer that I had packet loss. If I received, in the case of the algorithm as is normally implemented, if I received 3 separate acknowledgements for an older sequence number, namely 0, then that is enough information for me to infer that sequence number 1 got lost in transmission. Right? And just having those duplicate acknowledgements doesn't only tell me that I had some sort of packet drop, it also tells me which packet got dropped. Because I received 3 acknowledgements for sequence number 0 means sequence number 1 never arrived at the destination. So I can opportunistically retransmit that. This is what's called TCP Fast Retransmission, and it is probably the single most important optimization in TCP that actually allows us to have workable network communication over unreliable heterogeneous networks. Yeah, we just covered this. Okay, let's sidestep this a little bit. We have some notion of how sliding windows work. We have some notion of how retransmit works. And you will notice that we have a lot of different interesting variables here. So TCP is a very dynamic, adaptive protocol. It adapts to the situation on the network as it evolves. There are a lot of different variables that come into play with respect to how TCP determines things like window sizes, retransmit timeout, etc. These start with the round-trip time. And the round-trip time is something you can measure already at the connection level. Like once you've established the TCP connection, you have a sample for what the round-trip time is. But as all of you know, because you've been using your iPhones and your Android devices and your Macs in conferences such as this one, there is a lot of variability in round-trip times. If you just start a ping, right, just type in ping google.com on your laptops right now and let it run for a few minutes, you will observe that whereas most packets make their way to google.com in whatever, let's just say 20 or 70 milliseconds, some packets take upwards of a second and a half. Some packets take 500 milliseconds. There's a lot of variability. In fact, this is a graph of not at this conference, but at a different conference, just that measurement. I just pinged google.com and I charted the round trip time that I got for those packets going back and forth. And you will notice that even though it's relatively stable at around 10-ish milliseconds for that particular Wi-Fi connection, and it was a very good Wi-Fi connection, by the way, there's still a lot of variability. It spiked up to easily 270 milliseconds, and it did that, and it does that all the time. So the round trip time, being one of the things that are most important to figuring out the dynamics of the protocol, the situation on the network, is also dynamic in and of itself. It needs to be tracked as time evolves. So the TCP stack actually keeps track of this on literally every acknowledgement. Every acknowledgement gives us a sample for the round trip time, which we can keep track of in order to, through some statistics and nice mathematical formula, actually take in and determine what the effective round trip time is, which we might use to calculate a whole bunch of different things. There is also the maximum segment size. This is actually a fixed number, like it gets determined once per connection and it doesn't generally change. This is the largest segment you can send through TCP in bytes. And you've probably come across the acronym MTU, or maximum transfer unit, in just your everyday work. If you haven't, good on you. If you have, I feel for you. But the maximum segment size and the MTU, the maximum transfer unit, are related but decoupled metrics. MTU is a physical Ethernet level metric that tells you how big of a thing you can put on the wire. MSS is a related concept in TCP that tells you how many bytes can fit in a packet. What is the biggest packet you can send through the TCP network? Anything beyond that, you have to break down. You have to break down into multiple packets. So that's also an important metric. And then we get to the really dynamic stuff, like window size. TCP window size is, you actually have two of these for every TCP connection. Because if you recall, a TCP connection is bidirectional. It's actually two connections, one between host A and host B, and one between host B and host A. And critically, the networks are not symmetrical either. So you can't assume that the number of things you can put on the wire going from A to B is the same as the number of things going from B to A. A simple way of thinking about it is you have your DSL connection that can say upstream 3 megabits per second. I can flat out guarantee you that Google servers, when you go to YouTube, have more bandwidth than that, right? So the networks themselves are totally asymmetrical. It means that the window size is totally different for each side of that particular connection and is kept track of separately. Now, the TCP window size is advertised on each packet. Part of the TCP header for a packet is the window size that I, as a receiver, when I send out an acknowledgement, I tag it with my receive window size, the amount of data I'm willing to accept. And how to arrive at that number is also the subject of years and years of research. Like, you can give not me, because I don't understand that, but someone who does, a network engineer, say, should be able to give you an hour-long presentation just on how to arrive at a good TCP window size. So, like I said, very big, very complicated topic. And then we have the retransmission timeout, which is also another dynamic variable that is adjusted based on the round-trip time, and how to arrive at a good retransmission timeout time so that you actually have that desirable flow control, the maximizing the use of the network and also avoiding overwhelming the receiver, is again a pretty broad subject that is subject to much research. Now, this is all just to give you some idea of just how dynamic TCP is and how complicated it is when you just wanted to send your stupid packet from one end of the internet to the other. But generally, you don't have to worry about it because it is, quote unquote, a solved problem. Smart people have done the research. They have figured out good algorithms for it. Those algorithms have been implemented over the last 30 to 40 years. So this is not a thing we have to worry about. But it is something that can, and in extreme situations where you have big systems at scale that try to push a lot of data around, you will run into these things. So it's worth knowing just a tiny little bit about them. So take a deep breath. You've made it this far, right? We've covered a lot of ground. It's time to wrap things up. Can I talk to my mom yet? Right? We have some idea of how TCP works. Is it enough to talk to my mom? Almost, because there's one thing we haven't covered yet, and that is how to close the connection. Right? We've opened the connection, we have the sliding windows, we have packets running around in a way that maximizes throughput, everything is good. Now we're done. We want to close the connection. As I mentioned before, a TCP connection is a conversation. It's a phone call. And a phone call needs to have some sort of handshake, some sort of conversation, and some sort of ending. When I, as a participant in a TCP conversation, wish to end the phone call, what I do is I send a FIN packet to the other side. Now, a FIN is a promise. A FIN is not something that once I send it, the TCP connection is dead. That's not how things work. A TCP is me telling the other side, I'm done. I have nothing more to say. For my money, I'm done sending. I promise I will not send any more data on top of this connection. And a FIN has a corresponding acknowledgement. Acknowledging a FIN packet, in effect, means that the other side of the conversation says, I have received everything. Because a FIN is just a packet, also has a sequence number. If that FIN had been acknowledged, it means that everything that was sent before that FIN was consumed and processed and acknowledged as well. So acknowledging a FIN basically means I now have received everything from you. I might not be done yet, but you're good. Like, I know I have everything I need from you. Both sides must signal a FIN. Why? Why is all of this necessary? Well, to start with, because it's polite. Right? If we said that TCP is like a phone conversation, you don't generally end the conversation with your friend, let alone your mom, by slamming the phone down and just walking away. Right? That's totally impolite. You want to let the other side know that you are done with this conversation. What happens if you don't? Well, if one side terminates the connection, by which I mean if A sends enjoying build stuff to B, and B has just decided that it's no longer part of this conversation, well, actually, I got the sorry, I got the example wrong. Let's say A sends that message to B, and then the connection drops. A decides that it's not waiting for that response anymore. And then at some point, because the network is async, B sends back a yep. Computers are kind of dumb, right? They don't ahead of time know how to make sense of things. So if I'm a computer, I'm part of the conversation, and I dropped that conversation, like I've eliminated all state of that conversation from my memory banks, I no longer have the concept of that conversation ever having taken place. What happens if someone just sends me a packet randomly? Well, if someone sends me a packet randomly that's not part of a pre-existing established connection, well, I send a reset packet. And a reset packet is basically saying, huh? And that has the ramification of actually showing the message connection reset by peer that we all know and love. So B, in response to that reset packet, will go like, I don't know what happened on the other side, but that dude is an asshole. Like, he does not care about having a polite conversation with me. And that is basically slamming the phone down. That is not how we want to do, how we want to communicate. More importantly, though, if you think about it from a technical standpoint, let's suppose you emit an HTTP put call in one of your RESTful services. How do you know for a fact that that call made it through? Like, even if you don't wait for some sort of explicit application level acknowledgement, you want to know that the message got through before slamming the phone down. Otherwise, you have no idea what the state of the system is. You might be in an inconsistent state. Right? You need some sort of indication that the other end had received your message. So that is why this mechanism exists. Now, you might remember that the network we're building on top of is asynchronous. That means packets get dropped and they get reshuffled and they get delayed. What happens if an old packet shows up again? Whether because it's part of the conversation that got delayed, or maybe it's part of the conversation that got duplicated. What happens if you have that flow and everything works correctly? The conversation was shut down neatly, right? And that packet then arrives, and it doesn't seem to be part of any conversation at all. Even worse, what happens if that packet actually comes in before that whole FIN-ACK thing happened, and it does look like it's part of the conversation, even though it's the result of just a network condition? That's unusual maybe, but will inevitably happen. So this is not a very probable situation, because for this to happen, you need to have the same socket pair, the same host address and port address on both sides, and you also need to have the same sequence number, or like a corresponding sequence number for that packet to be considered part of the conversation. But the nice thing about the internet at internet scale is you take something that has a very low probability and you just let it run for a sufficient length of time at internet scale, then it becomes inevitable. Every failure mode you can imagine, given sufficient time and sufficient scale, will happen, including this one. So the TCP protocol also includes provision to deal with that. When a client connection closes, when I'm a client and I close a connection, I actually in terms of the TCP stack doesn't just take all of what it knows about the connection and throws it away. It keeps track of it for a certain grace period. This is what's called time wait state. Now, if you've run netstat or any of those tools to look at sort of what open sockets you have in your computer right now, you will undoubtedly run across multiple sockets that are in this time wait state. And what the state is the TCP stack giving a grace period for the network to screw up so that it can then take in those packets, make sense of them as having belonged to an older conversation, and throw them away instead of responding with a reset packet. A reset packet, as a reminder, causes a connection reset by peer message to appear on the other end of the conversation. As an example, if you just take a DNS client and you show google.com's DNS address, IP address, and you start a connection through whatever means, in this case it's an HTTP client, And then after that conversation is done, you have finished this HTTP conversation, but then you look at your list of open sockets, you will find a connection to that address at port 80 in time wait state. And the reason that happens is exactly that. So if you close a socket on your app, what happens is that you might have some stuff still going on. Right? The fact that you told your socket to close doesn't actually mean that anything happened on the underlying asynchronous network. There might still be packets in transit. There might be acknowledgements coming back in the other direction that you haven't processed yet. So what do you do about it, right? What happens between calling close on the socket and those things arriving at your endpoint? Well, that's what SO linger is for. If you have SO linger set up by default, which is what we generally do, then there's this grace period by which the TCP stack on your end can take in those delayed packets and drop them safely, because it knows the context of the conversation. It knows that it can safely just drop these acknowledgements or not respond to them or any of these things. Now, if you look at Stack Overflow or a bunch of places and you Google for time wait, like I have sockets in time wait, what should I do about it? It's weird. You will oftentimes have people recommending to set SO linger to 0. And the result of that is that it actually circumvents the normal TCP shutdown mechanisms. What this means is that as soon as you shut down close a socket that's set for SO linger 0, then anything coming in from the network on that socket pair at that point gets an RST packet sent. Like your host will respond to anything happening after the socket close, any inbound acknowledgements, any sort of leftover stuff on the network by sending out a reset packet, causing connection reset by peer on the other side. And that's not a very good idea. That's not how you want to go about it, because it confuses the hell out of everyone. That is why sometimes when you have crappy client libraries, you actually observe in your logs, in your app, so many connection reset by peer warnings or errors, depending on how it handles it. So just don't do it. Like, there's no reason to it. Once you have a reasonable understanding of how TCP works, you no longer have to apply these hacks, and you can actually make use of those mechanisms as God intended. I will leave you, obviously the slides are going to go out on Twitter, etc., so you're going to have those links. If you want to research more into this very, very broad and complicated subject, then there are a number of useful resources. I would recommend these 3. You will notice that because it's such a big subject, we haven't actually covered a whole lot of it. We haven't talked about delayed acts or Nagel's algorithm, congestion control, all of these things we have not touched about because it's so big. But I hope that you now have some intuition as to how TCP works and why. And because we're out of time, if you have any questions, catch me afterwards and enjoy the conference. Thank you very much.